Thank you for inviting me to this nice conference. I'm very glad to present my talk on material curation, which is interdisciplinary utilization of scientific principles, knowledge for materials R&D. My name is Michiko Yoshitake from National Institute for Material Science in Japan. I first talk about relations among material properties with some examples which are based on scientific principles and show relations with data plots. Then, the construction of database of materials property relationship is explained, and how the database search system is combined with laboratory automation is explained. At the last part, demonstration of the system will be shown. I first would like to emphasize the importance of interdisciplinary thinking. When electric device, solar cells, and so on is developed, the device material is sandwiched with high work function electrode and low work function electrode, and up to electrodes, low work function electrode material without high reactivity is not so common. Transition metal carbides are good candidates, but carbon deficiency influences work function, which is not well known. We revealed the effect of carbon deficiency on work function is predicted from viscous hardness. This is how the work function is related to viscous hardness through many other properties. Here we have different fields of material science to make those connections. And it is usually difficult to find such an interdisciplinary relationship by individuals. This is an example of making a relation through scientific principles. This is an example of formation enthalpy versus band gap energy when A atom and O atom binds to make molecule. It makes bonding orbital and antibonding orbital, and electrons from each atom goes to binding orbital, and energy is stabilized, which is equal to the formation enthalpy of molecule. And for the simplest case, this formation enthalpy is equal to homologue gap. Likewise, when atom binds together to make solids, instead of molecular orbital, it makes bands, valence band and conduction band, and the band gap is formed. But the principle is similar, so that the formation enthalpy of solid is expected to relate with band gap. When the formation enthalpy of some metal oxide and band gap are plotted, it looks scattered, but when the formation enthalpy of oxide is normalized by metal balance, then it shows good linear relationship. This is another example about binding potential versus permittivity, which is direct constant. When the electric field is applied, the electron cloud deviates because of the electric field, and it makes the dipole moment. When the ion coil and electron distance is plotted as a binding potential, the binding potential is shallow. The increase of this electric potential by electric field causes the larger electron displacement, means that larger dipole moment and larger permittivity. So the shallow binding potential means weak binding, and which means that the small formation enthalpy. As we see before, the formation enthalpy is small, then the band gap is small. And then this shallow binding potential causes larger permittivity, so it turns out that the small band gap corresponds to larger permittivity. In fact, when we look at the NANIMS database AtomWork Advance and plot the permittivity versus energy gap, it shows really trade-off relationship. So we saw that the formation enthalpy, Moore gap, and band gap, and the formation enthalpy and permittivity related. In the similar way, we can connect many different relationships among different material properties. So we dream up the making of database of material property relationships, but not manually, but automated way. We collaborated with a company and made a system so that we put a textbook on material science so that the computer can automatically extract relationship between material properties and make the database of material property relations. Then the user can search the material property relationship with the database. And also, if user have the specific relationship input, then this relation is connected to this base relation in the system to merge, and the user can search this merged relationship database. This search system has two different types of search. One is the connections between two properties, how two properties are related through other properties. If you have trade-off between two properties, by searching this way, one may find why those two properties are trade-off. Another way is to search the target property around which property is connected. With this way, sometimes one can find an unexpected interdisciplinary relation to control the target property. This is an example in the system with already mentioned relationship between formation enthalpy and band gap. The binding energy here, as we see how this two is related before. And this is the permittivity and band gap relation. Here we also can see the connections in the system. This is another example on organic material about solubility parameter and glass transition temperature relation. Actually, when you look at the NIMS database for info, it's a polymer database. Glass transition temperature and solubility parameter are very good linearly dependent. In the system, if you click the edge which connect to material properties, then name of book and phrases where the relationship is stated are shown like this. And if you click one of them, the complete phrases taken is shown. Next, we'd like to talk about this search system combined with laboratory automation. Nowadays, machine learning is very in fashion, and with this technique, one can make an automated development of material by this loop. In this loop, sometimes when one wants to data input from the database, it often happens that data is missing for the particular material. This material property relationship database can suggest which other material property can be used to compensate the missing data, or which descriptor should be added to this loop. Another way to use this material property relationship database is when the optimized material is output, sometimes it's not known why this material is good. The database search system can help to explain why it is good. When one has this loop, one has to first design the material or the aim to make this loop manually by human. For this individual knowledge and experience, it's used usually, and this material property relationship database can help the people to design the materials or the system to explore. This is a demonstration. This is the top page of the prototype system. There are two main functions, path search and network for searching relationship among various material properties. In path search, user input two material properties, for example, barrier height and thermal expansion coefficient, and click search button. Then how the two properties are related through other properties are displayed. In network, users input the target property, let's say glass transition temperature, and click search button. Then properties relating to the target property are displayed. By double-clicking one of the related properties, for example, rigidity, related properties to rigidity are further displayed. User can go further another property, let's say shear modulus, like this. The searchable database of material property relationships, called Material Curation Support System, are under development to release as a product at Fujitsu. If one would like to have explanations on the product or want a trial, please contact Fujitsu to this email address. Thank you very much for your attention.